It's Gabriel Lord from Heriot-Watt, and he'll be telling us about numerics of stochastic porous media.
Okay. Thank you very much for the invite here and the opportunity to speak. So I should start with an apology. I think 4 or 5 people have now asked about movies that they're going to see, but there are no movies. But please don't leave. So with a background in numerical analysis, all my pictures tend to end up as straight lines. So all of these nice numerics are just going to be straight lines at the end of the day. So this is joint work with a PhD student, Antoine, who's in mathematics, and he's working joint with me and Sebastian, who's in the Institute of Petroleum Engineering. That doesn't mean that he's responsible for BP or anything, but it does mean he's got a real interest in looking at porous media flow, not just for petroleum, but also for things like carbon storage, and waste treatment type applications. So what I want to do is to extend recent ideas by Arnulf Jensen and Peter Kloeden, where they're using linear functions of the noise in their numerical approximations. They did this really for Fourier discretizations. I want to extend this to look at finite element and do some applications using finite volume discretizations. And at the same time, I want to look at these exponential-based integrators. Now, there's a good chance that I've lost all the audience already, but that's all right, because I'm going to tell you what these ideas are, and I will tell you what these type of integrators are. So by the end of today, if nothing else, maybe you'll remember at least another way of doing a numerical integration. So I want to start by just very quickly going through the motivating example of the porous media flow. I'll talk about how to use these linear functionals of the noise. I'll show you some theorems on convergence, and then the last part of the talk, the last half of the talk, will be on some numerical simulations, and in particular I'll just talk at the very end a little bit about how to implement these types of numerical schemes. So this is the nicest picture I'm going to show you, which hopefully you can see has got a mix of blue and red on it. This is a concentration of some solute which sits here, it's injected here, and what we're interested in is when does it arrive at this left-hand endpoint here. Okay? So this might be, for example, some horrible chemical that's being stored in the ground, and we're worried about when the red for danger is going to start contaminating our water supply. Or it could be that this is water and we want it to come out of the rock at the other end. This is a simulation, this is a deterministic simulation that we've done for this equation here, and it's done using what is a test example in the porous media community, in the petroleum community, called SPE10, and what they give you is the geometry. So one of the things that you'll notice is that this is not a nice diffusion where everything's happening in nice concentric fronts moving forward, diffusive fronts moving forward. We've got this advection term, and this advection term means that we've got regions where there's very fast transport of the solute. Okay? So I've got essentially a reaction diffusion equation with this advection term, and the way that we get the Q, I'll describe in a minute. The reaction term is this Langmuir absorption, and what that models is how much of this chemical that we've got here is taken up by the substrate, which is rock, as we go forward in time. D is constant. I'll take D to be constant for this. Okay, I've hidden actually a porosity which I've divided for this simulation. In fact, we've divided through by D is not constant for this simulation, but for the numerics, what we're going to have is D. For this talk, D will be constant. So how do we get this velocity Q? Well, somebody, SPE10, gives us this permeability, and then there's an assumption that the rock and fluid are incompressible. There's mass conservation, and that gives us this velocity Q. So for most of this talk, I'm going to assume that we've been given some Q, some vector here. Okay. Now the flows might be advection dominated, so there might be regions of very fast transport, but there might also be regions where there's almost no transport as well. Okay, so there might be, and everything is just diffusion. Okay. So this is a tricky problem to solve. So one of the things that we're working towards doing is taking this PDE and adding on some noise, partly because we can, partly because it makes an interesting example for us. So if I talk to Sebastian, okay, he's more interested in what is this going to give him for his simulations, what's he going to be able to get out of this. So the way that Sebastian is thinking about this is we're trying to model, for example, you might be modeling the uncertainty in the permeability. So that would come through into this term here. So he'd really like me to have noise acting here. That's not what we're going to do now. We're just going to look at simple additive noise. So this is just going to be phenomenological. P is the pressure, which I haven't told you what that is. So you set up a pressure field across here, so there'd be a region of higher pressure and lower pressure, which gives you this gradient. Okay, so we're going to take this an additive noise term onto here, and we're going to have the idea that we've got solute that can move and solute that can't move, and this additive noise, small additive noise, is going to give us some transfer between solute that can and can't move. This is our first approximation anyway. So I'm going to take this stochastic PDE and I'm just going to write it in a more useful notation. So let's just generalize this to linear operator A for the diffusion, some nonlinear term where we'll put in together the advection term and the reaction term, and then some noise. And we'll take A. A's got to be a second order operator, in fact, for this talk. And what do we have on the noise? So we're going to represent the noise in terms of the eigenfunctions and eigenvectors of the covariance operator Q. And for convenience, let's assume that the eigenfunctions of A and the covariance operator Q are the same. And we're going to look at noise which is spatially correlated. So I think throughout this talk I'll either take noise to either be in H1 or in H2 in space. So I'll have polynomial decay of the eigenvalues Qi. If by mischance there's a picture which has something different, then it's got exponential decay of these eigenvalues. For our model, what we'd really like to do, or what we're planning to do, is to take correlations which correspond to the correlations that we've got in this field here. Okay. If you've been to a talk on stochastic finite element, stochastic Galerkin type collocation or Galerkin type methods, they would often be looking at solving this equation here with the K being a random field. So we're doing something slightly different. So when I'm talking about stochastic porous flow, I'm thinking about this equation here. So we can take this equation and we can write down the mild solution of this equation, and this is what I'm going to use a lot for developing the numerical schemes. Okay, so now I want to describe this idea of using a linear functional of the noise. So I want to get a numerical scheme. So I'm going to use going to start off by discretizing in space using a Fourier discretization. So I'm going to project my solution onto a finite number of Fourier modes. Okay, and I'm going to have an equation that evolves in Fourier space. So that's all I'm doing here is I'm defining the projection onto a finite number of modes. I can also project the linear operator A and the semigroup. Okay. So that just gives me this discrete evolution equation. So it's finite dimensional. Okay, so now I want to discretize this in time. Okay. So just for ease of exposition, let's just ignore the nonlinearity. So let's take that out and just look at the stochastic heat equation, just so we can see what happens. There's the mild solution for the stochastic heat equation. Now I want to get a numerical method. So what I want to do is to look at, so I've already done that, so this is looking at taking the solution from time tk and giving me a solution at time tk plus 1 using the mild solution. Okay, I'm now going to I'm going to approximate this in using Fourier space. Okay. So what's a standard scheme for this? Well, a standard numerical scheme. Okay, let's actually look in each Fourier mode. So I'm going to call the Fourier mode VIK, so the ith Fourier mode at step k. Standard scheme. What do you pick up from the semigroup? You just get e to the lambda I delta t. That's from this operator here. Plus, okay, so we need to approximate this semigroup here. Let's approximate it at this left-hand endpoint. You get an integration over this interval, so we just get a standard Brownian increment giving us this term here. So that would be a standard type of discretization. But this is just an OU process in the Fourier modes. Okay, so here we did nothing to get the variance correct. We just used a standard Brownian increment. But what we could do is to get the variance correct and use this for the Fourier mode. So that's the nub of the idea. Okay? It's a nice straightforward idea, easy to understand after a heavy meal the night before. Okay, so you can then start to think about, okay, why does this work nicely? This works nicely because in Fourier space, everything becomes a diagonal operator. Okay, so it's very efficient to implement, and you can use it. So Arnulf and Peter, they have a theorem on the convergence. So there's strong there's a strong error estimate here. And what does it say? Well, it says that the error goes like the eigenvalue to some power of log of the number of time steps that we take divided by the number of time steps that we take. Okay, so we can estimate log m, and we get strong order of 1 minus a little bit. Okay. So the other thing that Arnulf and Peter look at is what's the cost that you need. So how many operations does it take to actually achieve this at some final time? So the cost goes like m times n. So n is the number of Fourier modes that I'm taking. M is the number of time steps that I'm taking. Okay, so it goes like m times n operations to get my solution at time vk. You can then ask what's the optimal scaling that you need here for the error. Okay, so m should go like k, the cost to the third, n should go like cost to the 2/3, and you'd get that the error is like cost to the power minus a third. So we get an order of the scheme in terms of the cost. So this is for space-time white noise. So Davy and Gaines showed that for space-time white noise, if you're using equidistant values of your increments, then you shouldn't be able to converge faster than a sixth. Okay, so where's this extra bit come from? It's come from getting the variance correct. Okay, so we've used this, that little bit of extra work to get the variance correct actually gives you something which is very worthwhile. And it works nicely because the operator that you get is diagonal. Okay. So this then says, very nice, but I don't want to always have to be using a Galerkin approximation. So can we adapt this in some way for finite elements? So that's what we're going to do. So I now have to introduce my finite element discretization. So here's my equation. I'm just introducing these spaces because they'll come up, they'll be hidden on slides, but I'm not going to really mention them much further. If I've got Dirichlet boundary conditions, I just want to let V be the space of H1 functions which satisfy the boundary conditions. And if I've got Neumann boundary condition, let's take V to be H1 and H satisfies the boundary conditions. I'm going to look at piecewise linear finite elements over my triangulation, and in the standard way I'm just going to introduce another projection operator pH, which is the projection onto this finite element space. Okay, so now I can write this equation in finite element space, and what I'm going to use is I'm going to use the two projections that we've got so far, the finite element projection and the projection onto a finite number of Fourier modes. So I can rewrite this stochastic PDE as a large system of ODEs, or stochastic ODEs, like this. Okay, so I project onto XH is the finite element space. I've got this linear operator which gives a semi-group for the finite element space there. I've got projection of the nonlinearity, and for the noise I project onto a finite number of modes and I project that onto the finite element space. So this is the simplest way that I could think of, because I like simple ways, of actually using the ideas from Jensen and Claudon, and we're going to treat this noise, the noise term here, like it was treated before in the Fourier case. Okay, so now let me go through the numerical discretization. Sorry, the time stepping. So we start with a mild solution, for example, of our stochastic PDE. Let's discretize in space. So I've just changed all the operators from being the continuous operators to the finite element operators, and I've got the projection onto a finite number of modes. Now let's just look at how do we get our solution from time step tk to get our solution at time step tk plus 1. Okay, so I just want to look over one step. So let's look over going from 0 to time delta t. Okay, so I look at delta t, so t1 it should be delta t. I evolve the semigroup over time step delta t. There's my initial data from 0 to delta t, evaluated at the so t is just delta t, and so I've just rewritten this, and I haven't done anything yet. This is still exact. So what am I going to do? I'm going to have to approximate this part, and that we're going to do like we did before, and we're going to have to approximate this part. So let's approximate this f at the left-hand endpoint. Okay? So approximate f at this left-hand endpoint, we'll be able to pull it out, and we'll get the integral from 0 to delta t of the semigroup. Okay, well that's an integral that you can actually work out. Okay, so I've just worked out what that is. Okay, so we get this operator here. Okay. So we said we're going to treat f as being constant over a time step, evaluated at the left-hand endpoint. So let's pull that out. So that's pulled out of the mild solution there. This integral we can do. So that integral there is given by this term here. So we get as our scheme, we need the exponential of e to so the semigroup acting on our last time step, the flow forward using this phi1 function, which is an approximation to that integral there, plus the noise. So that's hopefully it's clear that you could just take the mild solution, approximate stuff, and you end up with a scheme. Okay, that's all we're doing. At the end of the day, I am going to do some numerical simulations. So one thing that I don't like here is I've got the exponential of something which is going to be this is going to be the exponential of a matrix, and here I've got some function which is an exponential of a matrix. Okay, so it's just a little bit cleaner if I can write it in a more efficient way. So if I add in and subtract out xm, so the previous time step, okay, then I can pull this thing into this phi1 operator, okay? Yes. So at the expense of multiplying by the linear operator a. Okay, but that's just a matrix vector multiplication, so that's easy to do. Okay, so that's cheap, that matrix vector multiplication, and it means that I just have to compute one of these things here, this once. Okay. In fact, when it comes to real simulations, you don't form this matrix. Okay, that's too expensive. What you do is you work out what the action of that matrix is on a vector. So we'll be looking at this as a vector and working out what its action is. I like the practical part of actually getting it to work nicely, okay? But there is something to having a theorem or two that goes with it. So here's we've got a couple of theorems which show that the scheme works, the convergence of this. I'm going to show you them. I'll give you a quick sketch of the idea of what the proof does. And what time am I meant to shut up? 10 after. Ah. Okay, so I'll shut up and start pressing this button. Yeah. You you might just want me to shut up anyway, but that's okay. So I'm going to this is a cut down version, theorem light, just so that you can see what the results look like. Theorem heavy is on the next slide, but it's got more conditions and it's a bit ugly. Okay, so let's just suppose that f satisfies some globally Lipschitz conditions. I'm going to get an error estimate in H1. I want my domain and my triangulation so that I can apply this standard finite element inequality. Okay, so that would say that if I've got a function, I look at the finite element projection of this function in L2, I can bound it by some constant times the mesh step. If we take noise in H2, then if I start with data which is sufficiently smooth, so this is starting with data being in H2, then I've got a bound on the strong error, which is like, so it's in space, this is like H, I've got delta t to the half, and then what's this term? Well, this term comes from the projection, so this is the projecting onto a finite number of Fourier modes. Okay, if I take enough Fourier modes, I can bound this by H. Okay, so you can play with the number of your projection error against your spatial error. Okay. You can use, Stig's got lots of nice results on non-smooth error estimates. So this assumes that your initial data is sufficiently regular. If your initial data is not so regular, so if you're in L2 to H2, then you get an error estimate which blows up as you approach 0. Okay. So that's a standard estimate. Is there a question, or if I made a mistake? No. Okay, so that was the nice version. That's the theorem light. This is a slightly heavier version. This is for convergence in L2. Okay, so we've got some conditions on F and its Frechet derivative. Conditions on the norms on the noise. So noise either in H1 or in H2, and we get a very similar type of estimate with, in fact, a slightly better convergence in delta t. Okay. So again, we can split this up into whether you've got smooth initial data or not so smooth initial data. All these proofs go around in the same way. Okay, so we started by approximating the mild solution. So we can just split this up over all of the little subintervals that we've got, and then we've got solution of the random PDE part with the noise. Okay, we can look at the scheme in exactly the same way. So we've got the solution of the random part and the noise. So I'm going to call all of this stuff here Zm. What's the error? Well, the error, we just subtract them. So I've got that minus that. And the obvious thing to add in here and to take out is the projection of the noise onto a finite number of modes. Okay, so I've got the difference of the two random parts, difference of the projection of the noise in the finite element space, and the difference of the projection of the noise onto a finite number of modes. Okay, so this bit's like a finite element error, this bit's like a projection error, and all the hard work's actually in this term here. Okay, so on the next slide, I'm going to look at this term and this term because they're easy, and the 6 or 7 pages that it takes us to look at this term, we're going to sweep under the carpet. Okay, so what's the idea? I wanted to use that inequality which said that I could bound the projection error in the finite element space, so I do that, and we end up with a error estimate which is going to be like some constant times the mesh size to the power r. For the projection error onto a finite number of modes, that again goes in the standard way, and we get this term that comes out. Okay, so there's no big surprise here. Okay. Okay. I want to compare schemes. So I'm going to give you another scheme. If you didn't like my first one, I'll give you an easier one. Okay. Again, based on the mild solution, let's look at approximating this now over one step again, and let's say that we can't be bothered to do the integration of that, okay, of the semigroup. Okay, so let's not work out what that is. Let's just approximate all of this stuff at the left-hand endpoint. So that's what I'm saying here. So we get this. So this is just now, we're left with the integral from 0 to delta t of ds. And so we get this as another possible approximation. Okay? You can hit your head again, and you get the similar sorts of convergence theorems as our first scheme. Okay? There's a whole family of these types of exponential integrators. The two that I've shown you are the two of lowest order, and those are the ones that are commonly used for stochastic differential equations. Okay. Now you might be happier with something which is a semi-implicit method. Okay, so maybe you'd start with your stochastic differential equation and you'd approximate it like this, where here you're using the nice properties of the heat equation so that you could use large time steps, okay, for stability reasons. Okay, so you just rearrange that. We get I minus delta T AH acting on all of this, and so at each time step we've got a linear system to solve. Okay? What I want to do, I'm going to show you on the next slide, is just how to adapt this so that we can use the same trick that we used before of getting the variance correct for the noise. Okay. So again, what we're going to do is we're going to split this up into looking at the random part plus the noise, and we're going to write a semi-implicit method for the random part, for x bar. Okay, so this is this semi-implicit method for that random part of the stochastic PDE. Okay. So what's our approximation? Well, we approximate it as random part plus the noise, and that gives me this scheme here. Okay, and then this part we just get from our OU process. And we get the variance correct here, and then we do the projection onto the finite element space. Okay. Results, okay, we've got some convergence results here as well. They look the same, except you get extra terms. Why do you get extra terms? Well, the semi-group that you've got for this semi-implicit method is this. It's I minus delta T A. Okay, why? That's really a polynomial approximation to e to the delta T A. Okay, so you've got an extra approximation in there. We get extra terms coming into the error estimate. Okay, but okay, they essentially look the same. Okay. So now I'm going to stop talking about how we make these schemes and about the convergence, but actually show you them working, except there's no movies. So here's my two examples. This equation I like because I can actually work out what the solution should be. Okay, so this is a nice test example to check that everything's working, and then we'll look at this equation. So let's start. Everybody knows, or lots of people would have used, sorry.
Just a quick question about the previous slide. Q is independent from capital X, yeah?
Yes, yeah. So if you pick up a textbook, you will find the semi-implicit method given. Okay, so that would be your first port of call after finishing your numerical analysis course would have been a semi-implicit method. So I'm going to start by looking at what happens if we do this adaptation of the semi-implicit method. So here's my exciting numerical simulations of straight lines. This line here is the standard implicit method for this equation, solved using finite volumes. There are two lines here. They're the modified semi-implicit methods solved with two different space discretization of finite elements and finite volumes. This is the log of delta t, and this is log of the error. Okay, so that is an improvement in the error. Okay, so that's good news. The slope, I've got a faster rate of convergence down here than I have from up there. I can tell you what the numbers are if you don't believe me, but it is faster. In fact, the numbers I think are just off the bottom of the slide. Okay. I was expecting a woo, wow. But no, okay. We can do the same thing for the stochastic ETD methods as well. Okay, so this is that implicit method at the top. and I'm comparing here. Here's the modified one with this dotted line, and then I'm comparing the two stochastic ETD methods, both with finite elements and with finite volumes. Why am I doing finite volumes? Because at the end of the summer, we should be looking at some finite volume code, which is from Sebastian. So we want to check that everything that we're doing will actually work, although the analysis has been for finite elements, that it will all work for finite volumes as well. Okay, so we're getting a nice improvement in the convergence, and there's a difference between a line here and a line here. Now, it doesn't matter whether you could see which is which. I'm going to tell you. The lines that are here are the modified semi-implicit and the second stochastic ETD. Doing a little bit of extra work to get on the non-linearity gives me a small improvement in the error. Okay? This term here, this lambda is taken as being a non-linear term when I do these simulations. Okay. The order's 1. For this equation, it's 1. That's not true in the next one. Okay, so this is our more challenging example. So I want to look at a heterogeneous media. So I'm going to have some spatially dependent Q. So I'm going to solve for the velocity. So solving for the velocity, I need a permeability. So this is on a log scale. I've got 3 high permeability regions, okay, where the permeability is 2 orders of magnitude higher than the rest of the rock. Okay, so this is meant to be like fractures in the rock. Okay, so I need a Q. I solve this equation. I solve this equation. The elliptic equation. I find the Q. So this is using this mass conservation. That gives me the Q that I'm going to use in there, and then we're going to solve this equation, and we've got a mixed boundary conditions. Okay, so this is the velocity field that we get. Okay, so we see that there's regions of very fast flow and then regions of slower flow, and this is the deterministic solution. Okay, so you can clearly see the effects of having these 3 streaks, these 3 fractures where you've got flow which is essentially advection along here. Okay, so there's a input here, it diffuses along, reaches the region of high advection, goes through, and then diffuses out on the other side. Okay? This is the solution, or a sample solution with the additive noise. I think that might be the only solution that you're going to see. So then we can look at convergence of this. So this is now for the 2 stochastic ETD methods, and we've got convergence. We've got convergence with slope a quarter. Okay, so the theory predicted a slope of a half in this case. That was that first theorem that I showed you. We don't quite have that, and I think that's because of the velocity field. The velocity field's not quite smooth enough for the conditions that we've got, so I think we've lost a bit there. But it does converge. So to get these solutions, I want to talk just a little bit about some of the practicalities of implementing one of these exponential integrators. So if I've got a semi-implicit method, I ended up having to solve a linear system like this. Okay, I want to solve I minus AHV to get my new solution equals something. There are, again, you go to a standard numerical analysis course, you'll come away with a toolkit for solving this equation. There are lots of very good, fast, you could use algebraic, multi-grid, whatever, yes, parallelized, whatever. Lots of very different ways of doing that. That's not true for doing these matrix exponentials. Okay, so you have to think a little bit more about how to do this. Okay, so if I've got I need to work out what this function is. Okay, so what I really want is phi 1 v. Okay, I need to work out what the matrix that we've got here is acting on v. If when A is diagonal, this is straightforward, but we don't have a diagonal matrix for the finite element. Okay, so there's I think there's two competing methods at the moment that you could use. Okay, one of them's based on real leisure points, and there's a body of work describing this. It uses, oops, I knew there was a type of Dutch capital N. It uses a Newton polynomial approximation. Okay, so we want phi 1 acting on v. We want to approximate that. We use a Newton polynomial, and it's based on. So you have to find the focal interval. You have to take a number of points on that focal interval. Okay, so it should be real and complex, but the real leisure points just uses the points in the complex on the real line. You can use Gershgorin's circle theorem to get an estimate of that. So you need a large number of points to start with, and for convergence, you have to increase the degree of the polynomial. In forming this polynomial, you need to do some divided differences, and there's issues about implementing that. A lot of that seems to be becoming resolved, okay, but you do have to be a little bit careful. The other way that you might implement the matrix exponential is to use a Krylov subspace technique. Okay, so you project onto a smaller space, use a Padé approximation. In this case, you need to say how large a Krylov subspace am I going to take? And as far as I know, there's no a priori way of saying this is the right size Krylov subspace. And there's an issue about it. So we've used this Expo kit implementation of the Krylov subspace, and that's got an internal time step to get to some tolerance, which is another issue. Now, if I look at the timings of using BiCG stab in MATLAB for this, for the real leisure points and the Krylov subspace, they come out to be more or less the same. Okay, so I think these really are going to be competitive to doing something like the semi-implicit type method. Okay. This figure shows size of the system against the time that it takes. And really, I'm just going to look at one point on here. If I've got 10 to the 6 unknowns, okay, there's some scaling of the different Krylov subspaces. Here's the leisure point. It looks like the leisure point is very slightly faster, and okay, so it takes something like 25 seconds or something to do one step. This is in MATLAB on just a normal laptop. Okay, this is using different Krylov subspaces. Okay. So the message from this is you can do large systems. Suppose I've got roughly 500,000 unknowns, and I'm changing my time step, and I'm looking at the CPU time. Then we get a nice linear scaling with using leisure points. I'm using a large time step here. I'm using a large time step because what we want to do is to know what time does this solute break through. What time does our concentration actually get through to the other side? Nobody sets up nuclear waste dumps, for example, to just last 5 seconds or 5 hours or 5 days. We're looking more at 1,000 years, 2,000 years. Yes. So we want to do these predictions over much larger over large times. Okay. This barrier that we've got here. So these are large time steps. This is a time step of 100. This is a time step of 10. Most numerical analysis would be in this looking down here. Okay. And the last figure is just a comparison of the leisure points and the Krylov subspace for the heterogeneous flow that I showed. So this is for computing this figure here. Okay, so it shows that they both scale linearly. So here's the time, here's the error, and so for the smallest error I need the most time, but the scaling is really quite good. Okay, so that I think says that these methods are going to be competitive. So I'll finish there. Oh, yeah. So very simple, hopefully simple take-home message. I think doing this, just that little bit of extra work to get the variance correct, gives you something. Okay, there's not much that's for free in life, but maybe this and the dinner last night might have been it. I think the exponential schemes are practical, and we've got some convergence results that back that up, and some numerical simulations that show that this works. And we're currently working on an extension to multiplicative noise. So I'll stop there. Thanks.
Any questions?
I have a problem with your modeling. That means you take the additive noise, so your solution can become negative, in particular somehow close to -1 from time to time. And how do you deal with this potential difficulty?
Okay, so we haven't. Okay, in our simulations it did not come close to -1, but that would be an issue because you got the x over 1 plus x.
Yeah, that's what I mean.
So what we'd do is we'd use a boundary there. So we'd do some reflection, I think. That didn't actually come up as an issue in our simulation. But I agree. But it's a phenomenological model. It's not. I mean, it's work in progress. I'll change my nonlinearity if that's a real issue.
Yes. Okay, maybe so you have a noise that is diagonal in Fourier.
Yeah.
Then you take the projection onto a finite dimensional.
Onto a finite element
How do you do
space.
it? How do you calculate it?
How do I calculate? Compute. You mean? So there's two ways to. Okay, I do it both onto a finite element or onto a finite volume. Okay. So depending on which of these discretizations. So if you set things up nicely, then you get that your two grids will coincide. If not, then you have to do so you're using an FFT. So FFT to come back into real space from where it's all diagonal, and then you've got it at points, and then you may or may not have to do an interpolation. That's the practical way to do it.
More question? Yes.
I have a theoretical question. At least in your theoretical theorems, could you replace, I guess, you replace your finite projection by wavelet approximations, and it should give you pieces with results?
I guess, yes.
With
I haven't thought about that. No, we've only just finished doing this. But yeah, that would be interesting to look at. And in fact, I mean, I guess the theorems are there really for the projection error as a. Yes, no, you're right. That would be straightforward to look at. That's a good point. Thanks.
One last question in the back.
Yeah, Omar?
So I may have missed it. In 2D, what is your noise? What is the spatial?
It's an H. For the simulations I showed, it was an H2.
So it's
Spatially an H2, but white in time.
okay. And how do you choose the H? What is this H2?
Why did I take H2?
No, what is it? I mean, you have a correlation function. What is it based on?
Yeah, so it's based on the decay of the Q. Well, if you think of the form of the noise, I've got the sum Qi, phi I, beta I, and the Qi's, if they decay polynomially with the right polynomial decay, then it's an H2. That's how.
Okay, great.
Okay, thanks.
See you, Gabriel.
Right.